shall consider some problems today. Look at this question. For the following statements, either prove or give a counter example. Either say that they are true, and if it is true you have to prove, otherwise you must show it is not true. First statement is every finite subset of a non-regular set is regular. Look at the statement carefully. It says every finite subset of a non-regular set is regular. Any finite set, let sigma be the alphabet. See, when you say alphabet, alphabet is taken as a finite alphabet. Okay? Alphabet is a finite set of symbols. Now, a finite set over sigma star will have some words like W1, W2, Wn. It will have a few strings like this. It can be represented by the regular expression W1 plus W2 plus Wn. This is the regular expression representing it, and you can have a non-deterministic automata very easily for that. Start from Q0, W1 Qf, W2 Qf, W3 Qf, like that. You can have a very easily have a non-deterministic automaton for this. So, any finite set is regular. Any finite set is regular, whether it is a subset of a non-regular set or not does not matter. Any finite set is regular. So, the first statement is true. What about the second statement? P is equal to 1 star 0 plus 0 0 1 star 0 1, and Q is equal to 1 star 0 0 1 plus 0 0 1 0 1 star. They are equivalent. Obviously, they are not equivalent. Immediately you should be able to say that they are not equivalent, because this is something star, that means epsilon will be there, the empty word will be there. Here any string should end with a 0 1. This means that any string should end with a 0 1, that means epsilon cannot be there. So, epsilon will belong to Q, but epsilon will not belong to P. Any other string also you can take, but they are not equivalent. So, these are not equivalent. Take the third one. Let R denote a regular set, then the set consisting of all the strings in R which are identical with their own reverses is also a regular set. It is not that the question you must, the statement you must understand in a clear manner. If L is regular, LR is regular. This is true, and that is not the same statement as this. This statement means something different. What is L? L is a regular set. LR consists of all strings WR, W belongs to L, right? And this, once you have the state diagram for L, make the initial state the final state, make the final state as the initial state, and reverse the arcs, you will get the state diagram for LR. That is that. But this statement is different. What it says is, let R denote a regular set, then the set consisting of all strings in R which are identical with their own reverses is also a regular set. So, if L is a regular set, by this you mean something like L dash equal to W, W belongs to L and W equal to WR. If you define L dash in this manner, L dash consists of strings in L which are equivalent to their reverses, that is W should be equal to WR. Okay. This is different from LR, please remember, this is different from that. And is this a regular set? This is not regular, need not be regular set. So, take an example, L is equal to, take 0 star 1 0 star, or as a language it is 0 power m1 0 power n mn greater than or equal to 0. You can take greater than or equal to 1 also, does not matter. Then what will be L dash? L dash will be 0 power n 1 0 power n n greater than or equal to 0. If a string has to be equal to its own reverse, then this is not regular, right. You can use the pumping lemma to show that it is not regular. Okay. So, this is also not true. Every subset of a regular set is also regular. That is not correct, because suppose I take a power n, n greater than or equal to 1, this is regular. If I take a power 2 power n, n greater than or equal to 0 or something like that, this is a subset of this. We call this as L1, L2. L2 is a subset of L1, but that is not regular, is not it? L2 is not regular. So, this is how do you prove L2 is not regular? You can use the pumping lemma, you can use Myhill-Nerode theorem, or you can show that the Parikh mapping is not semilinear. If it is semilinear, periodically it should jump, but here the jump is not periodic. 2 power n then 2 power n plus 1 jump increases. Okay. So, in any one of the three ways you can prove. Okay. Infinite union of regular sets is regular. A finite union of regular sets is regular, because from regular expression, if L1 is represented by R1, L2 is represented by R2, L1 union L2 will be represented by R1 plus R2. That we know, we have seen while considering from regular expression to finite state automata, we have considered this. But the statement here is infinite union of regular sets is regular. So, define Li as a singleton a power I b power I. Li consists of only one string a power I b power I, right. If it has only one string, it is finite, so it is regular, is not it. Li has only one string a power I b power I, right. So, that is regular. L is equal to union I greater than or equal to 1 Li. This is an infinite union. I is equal to 1 to infinity, I is equal to 1 to infinity Li. I will write for each I, Li is just a singleton, and so that is regular. If you write L is equal to union I is equal to 1 to infinity, it is an infinite union of Li. And what is this? That is a power n b power n, n greater than or equal to 1, that is not regular, is not regular. Again you can use pumping lemma or Myhill-Nerode theorem. You cannot use Parikh mapping. Parikh mapping for this is semilinear, and it is a context free language. Here only context free language Parikh mapping is semilinear, here it is not even context free. So, you can use Parikh mapping for that. Oh, you can consider other, this is just one example, counter example. I am giving one example, you can give any other example. One slight deviation. So, if you consider CFL over one letter alphabet, you consider context free language over a one letter alphabet, what can you say about that? There is only one alphabet, A, sigma is A. That will be regular. Every context free language over a one letter alphabet will be regular, because if you take the Parikh mapping, ultimately it will be a periodic set of integers, and so you can write a regular grammar for that. Work out the details for this, try to work out the complete proof statement. Every context free language over one letter alphabet is regular. Okay. Next we shall consider this question. Find the regular expression for the set of strings on the alphabet 0, 1, 2 in which every 2 is followed by exactly 2 zeros and every 1 is immediately followed by either a 0 or else by a 2 0. So, if you have a 2, it should be followed by 2 zeros and you cannot have more zeros. I cannot have like this. And if a 1 occurs, it can be followed by a 0, more zeros also, there is no restriction here. Every 1 is immediately followed by a 0, but it can be followed by more zeros also, no problem. Or 1 will be followed by a 2 0. If 1 is followed by a 2 0, 2 should be followed by exactly 2 zeros. So, you can have only like this, right. So, what sort of substrings you can have? You can have 2 0 0, 2 0 0, 2 0 0 repeatedly occurring, that is possible. But if 1 occurs, it can be followed by many zeros or a 2 0. If it is followed by many zeros, there should be 1 0 at least, it can be more zeros. So, 1 0 0 star, or 1 should be followed by a 2 0, but 2 should be followed by exactly 2 zeros. Afterwards either a 1 or a 2 should occur. So, these sub patterns can repeat in the string, okay. Any number of them can be occurring like this, and in the beginning there, so this will represent strings where the substrings are of the form 2 0 0 or 1 followed by many zeros or 1 2 followed by 2 zeros repeated. But there is no necessity that the string should begin with a 1 or a 2, it can begin with a 0 also. Initially you can have many zeros preceding this. Right. So, this is the regular expression. Actually, in this case writing the regular expression is easier than drawing the finite state automaton and trying to write the equations and solving. You can draw the finite state automaton for that, but you must draw the deterministic automaton, then try to write the equation, solve, that is also possible. But in this particular example, this method is looking at the strings is much more easier, and you have to write the expression. Now let us consider one more example. Find the minimum DFSA for accepting strings over 0 1 with the condition that each string contains odd number of zeros or odd number of ones. Right? This R is inclusive R. If it is exclusive R, you will say it either odd number of zeros or odd number of ones. When you say odd number of zeros or odd number of ones, means it is inclusive R. The string also can contain odd number of zeros and odd number of ones, that is also allowed. What does that mean? It means that the string cannot contain even number of zeros and even number of ones. Okay? The string cannot contain both even number of zeros and even number of ones. And that particular example we have already considered, it is an example given in the book. Q0, Q1, Q2, Q3, 0, 0, 1, 1, 0, 0, 1, 1. I have not marked the final states. Actually, the whole class of strings is divided into 4 equivalence classes by the Myhill-Nerode theorem. You reach this state if you have even number of ones and even number of zeros. If you make this as the final state, that means the string has even number of zeros. And what is the complement? The complement will be this, this. If you have, if you reach this state, that means you have come across even ones, even zeros, even 1, even 1, odd 0, odd number of zeros you will get here. If odd 1, odd 0, you will go to this state. If you go to this state, odd, you have come across odd number of ones and even number of zeros. So, this diagram you can draw. The question is it the minimum state automaton or can you minimize? Now, if you follow the minimization procedure, I will do this. If you follow the minimization procedure, first you divide into non-final and final states. Now, what are the 0 successors of Q1, Q2, Q3? 0 successor of Q1 is Q0, Q2 is Q3 and Q3 is Q2. So, 0 successor of Q1 falls into a different block, Q2 and Q3 fall into a different block. So, Q1 will be separated now, Q2, Q3 are in one block. Look at Q2, Q3. What are the 1 successors of this? 1 successor of Q3 is Q0, 1 successor of Q2 is Q1, they are in different blocks. So, you have to split it. So, Q0, Q1, Q2, Q3. So, you cannot minimize it further, this is the minimum state automaton. But if the statement had been either odd number of ones or odd number of zeros, either odd number of zeros or odd number of ones, this will not be a final state, only the other two will be final state. In that case, the minimum state automaton will have only 2 states. The reason is, instead of saying this, if you have either odd number of ones or odd number of zeros, that means the other one should be even. If you have odd number of ones, number of zeros should be even. If you have odd number of zeros, number of ones should be even, that way. So, the length of the string will be odd, one is odd, another is even. So, the length of the string will be odd. So, actually in essence you are constructing an automaton which will accept strings whose length is odd, and that you can do with 2 states, is not it? You can have something like this. There you can merge these two, but not in the way we have considered. Let us consider one more problem. Every CFL can be accepted by a PDA with 2 states by final state. The acceptance is by final, accepted by final state by a 2 state PDA. It is enough if you have 2 states, you can accept every CFL by final state. Obviously, one should be the initial state, another should be the final state. 2 states means 1. How do you prove this? So, every CFL can be accepted by final state by a PDA with 2 states. Now, you know that we have considered the construction of converting a context free grammar into a PDA which accepts by empty store. So, from CFG to M such that n of M is equal to L of G, this we have done. And in this construction, how many states did we have for M? Just 1 state. So, in this construction which we consider, M has 1 state. So, every CFL can be accepted by a push down automata by empty store with just 1 state. Okay. So, I will write it like this. Every CFL can be accepted by a 1 state PDA by empty store. if we know that if something can be accepted by empty store, it can be accepted by final state. If M1 accepts a language by empty store, M2 can be constructed such that this accepts the same language by final state. This is empty store. This we know given M1 how to construct M2, given M2 how to construct M1, that also we have considered. Now given M1, when you constructed M2, you added 2 states, 2 more states, whatever be the set of states here, you added 2 more states Q0 dash and QF, right. So if you follow this procedure, then with 1 state you must add 2 more states, 3 states you will get, with 3 states you can do. But what you are expected to do is to do the same thing with just 2 states. So how do we do that? So M, I will call this as M. M is just one state Q, Q sigma gamma delta Q Z naught. It has got only one states and input alphabet etc. L of M is equal to L, the given language, every CF L. Now you construct M dash in such a way that M dash is QF 2 states sigma gamma dash, I will write it as gamma union gamma dash. What you have is gamma, every symbol Z in gamma you have a marked version, you have a primed version of it. So if you have k push down symbols, now you are having 2 k push down symbols. For every symbol, every push down symbol, you are having a marked version or a primed version of that. Delta dash we have to define. This Q is the initial state. Now Z naught dash, the primed version of Z naught will be the initial push down symbol and QF will be the only final state. How do you define mapping? The whole idea is like this. Whatever it is, you start with, in the original case, you start with Z naught. When you read the string, something will be done on the stack and finally everything will be erased. Okay. But now you start with Z naught dash, same simulation is done here except that whenever in the original thing you had, say, when the original automaton which is accepting by empty stores, at any stage suppose you have BM, B1, B2, BM on the stack, in this automaton you will have up to BM minus 1 the same thing, but the last symbol you always mark it, you will you use the primed version for that symbol. So ultimately in the last step when you remove this, you go to a final state. When you remove that primed version, you go to a final state. So the mappings are defined like this. If delta of Q A contains Q, there is only one state, please remember that, you have only this, Q is the same, M has this mapping, then delta dash Q A contains this, the same mapping will be here, and delta dash q a dash. Suppose the stack contains only the symbol a dash, then this should be replaced by b1 b2 bm, right, but the last symbol you will mark it. If this is marked, then it contains q b1 b2 bm minus 1 bm dash. Whatever mapping is here, it is also there, right. So, when the topmost symbol is not the last symbol, the stack contains more than one symbol, it behaves just, m dash behaves just like m. But when the stack contains only one symbol, it is a marked symbol. In that case, when you do something, you always make it a point to mark the last symbol. Then if you have something like this, if delta of QAA if contains Q epsilon, it is a popping move. You pop the symbol A, then the same thing you will have delta dash QAA contain, this map will be there in delta dash also. If you are popping something from the push down store which is not the last symbol, you have the same mapping, right. But delta dash QAA dash, if you are popping the last symbol which is a mark, then you go to the final state. Okay. So, with this sort of a construction, with 2 states, you will be able to accept any context free language by final state. Okay. S goes to ASS, S goes to B. For this grammar, let us consider the string A, AB, ABB, AA, BB, right. Is this the string? For this string, find the left parse, right parse and the Parikh mapping. That was the question. Now, the numbers, why are the numbers given for the rules? To find the left parse. What is a left parse? Left parse is the sequence of rules applied in a leftmost derivation. Right parse is the reversal of the sequence of rules applied in a rightmost derivation. What is the definition of left parse and what is the definition? It is not the drawing the I explained how it is used in top down parsing and bottom up parsing, right. That does not mean that you have to draw the tree, there will be only one tree. Please, is this grammar ambiguous or not? First of all, is this grammar ambiguous or not? Huh? It is not, it is unambiguous, right. So, for any string you will have only one derivation tree. So, for drawing one derivation tree, in the parsing how you draw the tree, and in the top down parsing, in the bottom up parsing how you draw the derivation tree is different, but ultimately you will get the same derivation tree, right. Left parse and right parse means this. left parse is the sequence of rules applied in a leftmost derivation. Right parse is the reversal of the sequence of rules applied in a rightmost derivation. So, if you consider a leftmost derivation ASS rule 1, then AS, this S is written as ASS, that is again 1 AA, then this S goes to B 2, this S goes to ASS rule 1, this is a leftmost derivation AAB A, then this S goes to B rule 2, another rule 2 have this, then rule 1 AAB ABB ASS. Now, this again rule 1 AAB ABB ASS. Now, these 3 S's will go to B 1 by 1, 2 2 2, you will get AA B ABB AA. See, when you want to get this string, when you want to see, first one A has been generated, second you have to generate A, that means you have to use the first rule only. If you have to generate B, you have to use the second rule. So, it is a sort of deterministic parsing. Okay, so, that is why it is unambiguous, grammar is unambiguous. So, what is the sequence of rules applied? It is 1 1 2 1 2 2 1 1 2 2 2. This is the left parse. Right? What is the right parse? Look at the rightmost derivation ASS rule 1, then AS, this is written as ASS rule 1 again, ASA, this goes to B rule 2, ASA, this goes to ASSB, this is rule 1, then 2 rules, 2 is applied to convert them into B, AS, AA, BB, B, then 1 ASS, AA, BBB, okay. AAS, this goes to ASS, AA, BBB. So, this S is rewritten as ASS, that is rule 1. Then AAS, ASB, AABBB, that is rule 2. Again, for this again you can apply rule 2, and again for this S you can apply rule 2. AAB, ABB, AABB, B. So, rightmost derivation the sequence of rules is applied, sequence is 1 1 2 1 2 2 1 1 2 2 2 1 1 2 2 2. The reversal of this is 2 2 2 1 1 2 2 1 2 1 1. This is the right parse. This is the leftmost derivation. At each step the leftmost non-terminal is replaced. The sequence of rules applied is this, and that is called the left parse. Here this is the rightmost derivation. At each step the rightmost non-terminal is replaced. The sequence of rules applied here is this. The reversal of that sequence is this. This is the right parse. And right parse is used for bottom up parsing, left parse is used for top down parsing. This particular thing can be parsed in a deterministic manner in a top down one. This is called, it has a LL1 grammar. This is a LL1 grammar. We say this grammar is LL1. Because when you have a S and a you know that you have to apply the first rule. When you have S and a B, you know that you have to apply the second rule. You can deterministically say that. That is why it is called L1. Another feature of this is there is something similar to the Dyke set. For this and the Dyke set, there is some similarity is there. Are you able to realize that? As the length of the string increases, see here at one stage you will have 3 S's, 3 S's in a sentential form at one stage, and similarly here also somewhere you will have 3 S's. Where is that? Here. As the length of the string increases, somewhere you will have to get 4 S's, 5 S's and so on. You cannot bind the number of non-terminals, somewhere it will increase like the Dyke set. So, this is not a language, the grammar generates a language which is not of finite index. L of G is not of finite index like the Dyke set. That is another feature of this particular grammar. This question what will be the how does it work on the string 110 110. You start in Q0. The stack contains Z0. How will this machine work on that particular string? Okay. So, I will write the string here 0 0 1. I am sorry, this 110 110. It starts in state Q0 reading a 1. So, on the push down store you have Z0. Then when you see a 1 you add a x. Again when you see this one you add a x. And in Q0 when you see a 0 you go to Q1. in Q1 you start removing the excess, in Q1 when you see a 0 you go to Q naught and in Q naught you can remove the symbol and the string will be accepted. So, this will be accepted by this machine. What is the language accepted by this machine? What is n of m? What is n of m? When you are reading a 1 in Q naught you are adding excess, then when you see a 0 you change the state from Q naught to Q1, and in Q1 when you read once you keep on removing the excess. So, the number of ones occurring before the 0 and after the 0 are the same. So, you will have 1 power n 0, 1 power n 0. Finally, when you read this 0 you go to the initial state, initial configuration again. Then what happens? First of all, is this machine deterministic or non-deterministic? Is this PDA deterministic or non-deterministic? It is non-deterministic. Even though these are all singletons, this is non-deterministic because when you are having a Q naught Z naught combination, you can have a true input move or an epsilon move. Both are allowed. In a deterministic machine, that should not be allowed. So, after reading this, you can erase the Z naught and end the whole process, or you can start again. So, when you start again you will get something like 1 power m 0, 1 power m 0. Again you can start again and get 1 power k 0, 1 power k 0 and so on. So, ultimately the language accepted is 1 power n 0, 1 power n 0 star something n greater than or equal to . You can just erase Z naught also. See, from this you can just erase that. So, epsilon also will be accepted. So, the language accepted n of m is something like this, or I can put it n of m is L star, where L is 1 power n 0, 1 power n 0 n greater than or equal to. Now, construct the grammar from this automata. Construct the context free grammar from this delta mapping.